Okay. Yeah, we start with an example of a closed set. Our set E is the set of all reciprocals of natural numbers on the real number line. That's the set E on the real number line with the usual metric, the absolute value metric. Okay? And then a subset F of E is closed. Equivalently what? So what I mean is how does every closed subset of this set E look like? Do you have any idea? For a subset to be closed, the subset must contain all of its contact point, right, in there. So then do you have any idea about how any closed subset of this set E looks like here? The subset F must be what? Must be a finite set. Yeah, those two are equivalent to each other on the set E on the real number line. You all already know that any finite set is closed, right? So this direction is trivial. How about the other direction? We can, describe the proof of the other direction using contradiction method. If F is not a finite set, in other words, if F is an infinite subset, F is an infinite subset of E, then because, this F is an infinite subset of this set E, this F must contain some sequence X of n converging to 0 in there, right? Because if F is an infinite subset of E, then what? The F must contain a sequence X of n converging to 0. Which means 0 is a contact point of the subset F. But since F is closed, the closed set F must contain one of its contact point is 0 in there. Right? That's a contradiction. That's a contradiction. That's a contradiction. Why do we have that contradiction? We have that contradiction because we supposed the closed subset F is an infinite set. So we suppose F is an infinite closed subset more precisely, subset of the original set E. Then because F is an infinite subset of this original set E, there is no other choice. The subset F must contain some sequence X of n converging to 0 because capital F has infinitely many elements in E here. So then that means what? 0 is a contact point of the closed subset F. Which means by the definition of the closedness, the closed subset F must contain one of its contact point 0 in there. Which is impossible. 0 is not in the original set E. So it cannot be happened. So we have that contradiction. Why do we have that contradiction? We have that contradiction because we suppose the closed subset F is an infinite set. So we must conclude any closed subset of E must be what? A finite set. So this is how every closed subset of this set E looks like. So any finite subset is closed. So which means this set E does not have the biggest closed set inside. There is no biggest. There is no biggest closed set inside E. Closed subset inside E. That's happened because every finite set is closed in there, right? So there is no biggest closed subset inside E at all. Yeah. Any questions or any comments about closedness on the metric space theory? So the next step is to study interior. Yeah, everything we study in this class may be reduced to what? The stuff we have studied in real analysis last year. If we reduce our, space to the real number line with absolute value metric, right? So, yeah. So let's let X with its metric D be a metric space. And let's let capital A be a subset of the whole metric space X. Then we say that a point X naught in the whole metric space X is an interior point of A. That's what we want to define. Okay, we have the whole metric space X with its metric D on it, and then we have some subset A of the whole metric space X, and then we say that a point X naught, okay, we say that a point X naught in the whole metric space X is an interior point of the subset A if there exists some positive number R such that open ball around X naught with radius R is sitting inside of the subset A. Yeah, that's the formal definition of an interior point of the subset A. Yeah, we have X naught somewhere on the whole metric space X, and then we say that that point X naught is an interior point of the subset A if there is some open ball around it. There is some open ball around it which is still sitting inside the subset A itself. Now, that's the formal definition of an interior point of the subset A. So let's collect all the interior points of the subset A. Yeah, the subset A may have what? A lot of interior points, right? So let's collect all the interior points of the subset A. That is denoted by this notation, A to the power 0, which is called the interior of A, interior of A. Okay, interior of the subset A, which is denoted by A to the power 0, is defined by the collection of all interior points of A. Collection of all X in the metric space X such that the point X must be an interior point. Of the subset A. So then the interior of A here has a lot of nice properties we will prove in the next step. Okay? First of all, let's note the following. clearly by the definition of the interior point, A interior must be a subset of the original subset A itself. That must be true, right? You know. First of all, right? Do we need some, justification of this? That's pretty much clear by the definition of the interior point. So, to prove this inclusion of those two subsets, so let's take any point X in A interior. Then, by the definition of A interior, the point X is an interior point of the subset A. By the definition of A interior. So by the definition of the interior point, there must exist some open neighborhood around X. There must exist some open neighborhood around X, which is still sitting in what? In the subset A itself, by the definition of the interior point. But the point X is in what? In this R neighborhood around itself. But this open neighborhood is in what? The subset A. So that means what? The point X is in the subset A. That's what we have claimed. So we have claimed that every element, every arbitrary element in A interior must be also in what? In the original set A. So that immediately implies this inclusion of those two subsets, which is pretty much clear from the definition of the interior point and interior thing. Right? Secondly, interior of some subset A may be empty set. This is possible. Can you raise up some example of the subset A in some metric space whose interior is nothing, empty? Well, on the whole real number line R, for example, on the whole real number line R, on the whole real number line R, with absolute value metric on, right? Let's let the subset A be the set of all rational numbers Q. The set of all rational numbers. Okay, set of all rational numbers. And then what is its interior then? Nothing. None of the real number is an interior point of the set of rational numbers, right? Because of the denseness of rational numbers and irrational numbers we have studied in the real analysis, right? On the real number line, this is the whole real number line R. And then take any real number X you want on the whole real number line R. Then no matter what neighborhood around that real number X we have chosen, that open neighborhood contains what? Contains both rational and irrational numbers. Contains both rational and irrational numbers in there. Right? So any neighborhood around X cannot be sitting inside the set of all rational numbers at all. So none of the real number is none of the real numbers is an interior point of the set of rational numbers at all. So the collection of all interior points of the set of rational numbers must be what? Empty set, nothing. Okay. And we prove, we claim 5 different nice properties about the interior thing in the next lemma. we again have a matrix space X with its metric D. And we have a subset A of the whole matrix space X. Then first of all, the interior of the subset A must be an open set. That is the first lemma we want to justify. How do we justify this openness of the interior of A? Using the definition of an open set, right? So let's let X be an arbitrary element in A interior. Then, by the definition of A interior, the point X we have chosen is an interior point of the subset A. Then, because X is an interior point of the subset A, by the definition of an interior point, there must exist some open neighborhood around X, which is contained in, which is sitting in the subset A. Then we want to claim this open neighborhood around X. Is contained in A interior. That's what we want to claim. Do you understand? The proof for the openness of A interior is done if we claim this here. We want to show this subset is open. For that purpose, we did take an arbitrary element in this subset at the beginning, and we want to claim some open neighborhood around that point is still in what? This subset. Then that means what? That implies what? That implies the openness of this subset, which was what we have desired. So we want to claim this open neighborhood around X we have taken on the previous step is in A interior. For that purpose, subproof. Let's let Y be an arbitrary element in this open neighborhood. Then, this open ball is an open set. By the definition of openness, there is some other neighborhood around Y. There is some positive number epsilon such that the epsilon neighborhood around Y is sitting in the open set, which is the R neighborhood around X. What does that mean? But this open ball around X, the open ball around X is in the subset A. Then what does that mean? Every Y in this open ball has some other neighborhood around it, which is contained in the subset A. What does that mean? That means what? The point Y we have chosen in that original open ball is an interior point of the subset A. In other words, the point Y must be in A interior. That's what we conclude. So what did we claim on this subproof? We have claimed that every element in this open ball is in this subset A interior. So then this inclusion was what? Justified in this subproof. Then let's go back to our main proof. What did we justify on the main proof? We have justified that every element in this subset, for every element in this subset, there is some open ball around it which is still contained in the subset. That was what we have claimed in this main proof. So then what does that mean? That means the subset here, A interior, is an open set, which was what we have desired. The second lemma is the following. This second lemma says, interior of A is the largest open set containing A. That's what the second lemma is about. The second lemma says, okay, A interior is the largest open set contained in A. Yeah, if you have a subset A on the whole matrix space X, and then what? We can have a lot of open sets contained in A, right? We can have a lot of open sets contained in A. Then what is the largest open set, subset contained in A? That is A interior. A interior is the largest open set contained in A. That's what the second lemma is about. In other words, if you take any other open set O contained in A, then the open set, any other open set contained in A must be a subset of A interior. That's what that means on the second lemma. If you take any open set contained in A, if you take any open set O contained in A, then that open set must be subset of A interior. What does that mean? That immediately means A interior is the largest, greatest open set contained in A. That's what the second lemma is about. So by the way, we must justify this inclusion. For that purpose, let's take any arbitrary element in the open set O. Then by the definition of openness, there must exist some open ball around X. Yeah, there must exist some open ball around X, which is still contained in the open set O. But open set O is contained in A, right? So what does it immediately tell you then? We did take an arbitrary element x in the open set O, and we have justified that. We have justified what? There is some open neighborhood around it still contained in the subset A, original subset A. That's what we have claimed here. Which means what? Which means the point x we have chosen is in what? Is an interior point of A, which means the point x must be in A interior. That was what we have claimed. So no matter what point in the open set O we have chosen, that point x is also in A interior. So that implies this inclusion of the subsets. Okay? Open set O contained in A must be in what? A interior. This second lemma immediately proves the next one. How do we rewrite A interior? Using set theory. That's what the next lemma says. From the second lemma there, how do we rewrite A interior set theoretically? A interior is the largest open set contained in A. A interior is the largest open set contained in A. Right? What does that mean? By the open set property, that A interior must be the union of all open sets contained in A. Is it correct? Yeah. So that's how we rewrite A interior set theoretically. A interior is the union of all open sets contained in A. We can immediately justify this rewriting of A interior set theoretically by the previous lemma. How do we justify this? You know, you easily recognize A interior is one of the elements in this set. Right? A interior itself is already one of the elements in this set. We know A interior is open, and we know A interior is a subset of A. Right? No. We already know that A interior is one of the elements in this collection. By the first note, A interior is a subset of A. By the first note, A interior is a subset of A. By the first lemma, A interior is an open set. So A interior is an open set contained in A by first note and first lemma. So which means what? A interior is one of the elements in this collection. So what? So trivially, A interior must be the union of everything in there. This line over here, okay? And this line over here is by the first note and the first lemma. By the first note and first lemma, A interior itself is one of the elements in this collection. By the first note, A interior is a subset of A. By the first lemma, A interior itself is an open set. So if we combine them together, A interior is an open set contained in A. So that means A interior is an element in this collection. So trivially, A interior must be a subset of all the unions in this collection. So the left side is a subset of the right hand side. How about the other? Why is the right hand side a subset of the left? That's true from the second lemma, right? That's true from the second lemma. The second lemma says every open set contained in A must be in what? Must be in A interior. That was the result of the second lemma. By the second lemma, every open set O contained in A every open set O contained in A must be in A interior. That was the result of the second lemma. So what I mean is every element in this collection is what? In A interior. That's what that means. Yeah, every element in this collection must be a subset of A interior. Every open set O contained in A must be in A interior. I must be more precise. By the second lemma, for every open set O contained in A, the open set O must be in A interior by the second lemma. So everything in this collection is a subset of the left-hand side. So then what must be happened to all their unions? And so trivially, the union of all those collections must be also a subset of the left-hand side. So we justified the left and the right-hand side is a subset of the left-hand side. But on the previous step, we justified the left-hand side is a subset of the right-hand side. So we concluded that those two subsets are identical. So those two subsets are identical subsets on the whole matrix space. Lemma number 4. What happens if A and its interior are identical? Then there is no other choice. The original set A must be an open set. That's the next lemma. A and its interior are identical. Then what? The original set A must be an open set. Yeah, this direction is trivial because by the first lemma we proved what A interior is open, but since A and A interior are identical, A must be open as well, right? Yeah, by the first lemma, it's trivially done. How about the other direction? We suppose A is an open set, and then we justify then A and its interior are identical. We already know that A interior is a subset of A, no matter how A looks like. That's true. This inclusion is true. From the first note, then how about the other direction? A itself is an open. A is a subset of itself and A itself is an open set. Then what do you conclude? A is a subset of A. This is a subset of A. Yeah, this is an open set contained in A. That's what that means, right? That's a kind of confusion, right? Yeah. How do you read out this sentence over here? This is an open set contained in that, right? Then what does that mean? By the lemma 2. What must be happened? The open set must be a subset of A interior. This is an open set contained in that, right? So by the second lemma, this subset must be a subset of what? Interior of the other subset there. But actually this subset and the other subset are identical subsets. So replace O here by A. That's what I mean. A is an open set contained in A. A is an open set contained in A. So let's replace O here by A in this second lemma. Then what must be concluded? A must be in A interior. A must be in A interior. That's what we must conclude. So we justified both inclusions. So we must conclude A and A interior must be identical. The last lemma, lemma number 5, is about the interior of A interior. You apply the interior to the subset A twice, and then must go back to the original set A itself. Sorry, it must go back to A interior. So the interior of A interior is what? A interior itself. That's trivially true from the previous lemma, lemma number 4. Apply the lemma number 4 to the subset A interior. Then we have this desired result, right? So replace A here by A interior. That's what I mean. Replace A here by A interior. So then A interior should be replaced by what? Interior of A interior, right? Yeah. Yeah, replace A by A interior. And then A interior must be replaced by interior of A interior. But because we know A interior is open, what must we conclude? A interior and interior of A interior must be identical, which is our desired result in lemma 5. Yeah. So I just say apply the lemma number 4 to the subset A interior, then we have this desired result. Any questions or any comments on Any questions or comments about interior thing? Yeah. Let's define a continuous functions. Okay, continuous functions in the metric spaces then. That's our next step. This is the generalization of the epsilon delta thing technique for the continuity of a function on the real number line we have studied in the real analysis last year. We have two metric spaces. X d1 and y d2. The first metric space is the subset X with its metric D sub 1, and the second metric space is the second set Y with its metric D sub 2. Both of them are metric spaces. And we have a function f from the first metric space X to the second metric space Y. And let's let x naught is a point, an element in the first metric space X. Then we say that the function f is continuous. The function f from the first metric space to the second metric space Y is continuous at the fixed point x naught in the first metric space X if no matter what epsilon neighborhood around f of x naught we have chosen. Yeah, that will have exactly the same structure as we already had in what? For the continuity of real value, the real variable functions we have studied in the real analysis. For every positive number epsilon we have chosen, depending on that, there is some other positive number delta of epsilon, depending on epsilon, such that if the distance between x and x naught is less than delta of epsilon, what does that mean? That means what? If you take any point x in the delta epsilon neighborhood around the x naught, right? In the D1 metric, on the first metric space X. That's what that means. Then the distance between the corresponding function values of f at x must be sitting inside the epsilon neighborhood around f of x naught. Yeah, that's the formal definition of the continuity. Okay? Continuity on the general metric spaces. So actually, if you have both real number lines with absolute metrics on both, then that definition is reduced to exactly what? The epsilon delta technique for the continuity of real variable, real valued functions we have studied in real analysis. So we, instead of absolute value metric, we use what? General metrics on both spots. Here is the first matrix space X with D1 metric on it, and there is another metric space Y with D2 metric on it, and then we have a point X naught in the first metric space X, and then we have a function f from the first metric space X to the second metric space Y. And then we fix a point x naught in the first metric space X, and then by the function f, we have a point function value of f at x naught on the second metric space Y there. then we say that the function f is continuous. We say that the function f is continuous at the point x naught on the first metric space x. If no matter what epsilon neighborhood around f of x naught we have chosen on the second metric space y, depending on that, there is some, I don't know how large it must be. There is some delta epsilon neighborhood around x naught in D1 metric, such that if you take any point x, in this delta epsilon neighborhood around x naught on the first matrix space x, its function value, f of x value, must be sitting inside epsilon neighborhood around f of x naught in D2 metric. That's a rough picture of, about the continuity of the function f between the metric spaces at a fixed point x naught on the first metric space. We say that the function f is continuous on the whole metric space x if the function f is continuous at every element x naught in the metric space x. So that is a natural extension. That's the natural extension of the continuity of real variable to real valued functions we have studied in real analysis last year, right? Well, the real number line is a special case of n-dimensional Euclidean space, and n-dimensional Euclidean space is a special case of a metric space we mainly study in this class, and the metric space is a special case of a topological space. So on the metric space, we have defined what? Continuity using what? Epsilon delta thing. Which was possible because the metric space has what? The metric on. Then how do we define the continuity in the general, more general topological space, which does not have the metric on? What is your idea for the definition of continuity on the more general topological space we will have in the future? Even if the topological space does not have the metric on, it still have what? On open and closed sets, right? So you remember the open set, the global continuity theorem we have studied in the real analysis, right? That must be used to define what? The continuity in the topological space. If you look at the global continuity theorem for the continuity, it doesn't need any metric or absolute value thing at all. If just open and closed concepts are in there, then what? We can immediately what? Use the global continuity theorem for the definition of topological space. You may have that in your mind. Yeah. So this kind of epsilon delta thing, techniques to define the continuity is malfunctioned on this general topological space because the general topological space may not have the metric on it, right? So we must have some other way to define the continuity in this more general topological space. So we will use what? The global continuity theorem to define the continuity on the topological space in the future. Okay, I think that's enough for today. Then let's continue about the continuity next week.